Welcome to a lesson on the chain rule for functions of several variables. This is part 1, and this part will deal with functions of two variables where both x and y are defined in terms of one variable t. In part 2, we'll take a look at when x and y are defined in terms of two independent variables. Remember from Calculus 1, if we have y equals f of u and u equals g of t, to determine dy dt, we found the product of dy du and du dt. And we can do something similar when we have a function in terms of two variables with one independent variable. What I mean by that is if z equals f of xy, x equals g of t, and y equals h of t, where z, x, and y are all differentiable, then dz dt is going to be equal to the partial derivative of z with respect to x times dx dt plus the partial derivative of z with respect to y times dy dt. It can often be helpful to use a tree diagram to remember the formula for the chain rule. For example, if we have a function z defined in terms of x and y, we would start off with a tree that looks like this. Z is defined in terms of x and y, and then x is defined in terms of t, so we'd have another branch here for t, and the same thing for y. Now once we have this tree, if we want to determine dz dt, we'd have to follow each of these branches to help us determine the formula for the chain rule. What I mean by that is, we'll start off at z and go toward x. This should remind us of the partial of z with respect to x. We continue down this branch and we encounter x and t, and this reminds us of the derivative of x with respect to t. And now we still have to follow the branch to the right, so we'll have plus, here we go from z to y, that's the partial of z with respect to y. And then we'll go from y to t, that'll remind us of dy dt. So the second half of the chain rule is going to be the partial of z with respect to y times dy dt. The nice thing about this is we can extend this, so if we had a function in terms of three variables, we'd have three branches, and if we had the variables x and y in terms of two variables, we just have two branches off of x and y. And we'll see that in the next video. Let's take a look at an example now. We're going to determine dz dt by using the chain rule and also by performing substitution to do a comparison. So we're going to find this derivative two ways and then make sure we get the same answer. Let's first write out the chain rule for this problem. If we want dz dt, it's going to be equal to the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. So we'll have dz dt equals the partial derivative of z with respect to x, so we're treating y as a constant, that'd be 2x, times dx dt, well x equals 2 cosine t, so we'll have negative 2 sine t, plus the partial of z with respect to y is going to be 2y times derivative of y with respect to t. Derivative of sine t would be cosine t. Now we want our derivative in terms of t, so let's go ahead and perform a substitution where we're going to replace x with 2 cosine t and replace y with sine t. Now let's take a close look at this. These are actually like terms. Here we're going to have negative 8 cosine t sine t plus 2 cosine t sine t. That's going to give us negative 6 cosine t sine t. Now just for an illustration, I went ahead and evaluated this derivative at t equals pi over 4. And that came out to negative 3. Now the reason I wanted to do this is because you could think of dz dt as measuring the change in the height with respect to the change in time at t equals pi over 4 on the surface generated by this function. And you could think of x of t and y in t as the path in the xy plane the particle is taking. Let's take a look at this. In yellow we have the surface generated by the function, and if I angle this correctly you can see the elliptical path of the particle on the surface given by x equals 2 cosine t and y equals sine t. It's an ellipse. So as t changes, you can view this blue vector tracing out what could be the path of a particle on the surface. And t equals pi over 4 is approximately 0.785. If I go back to 0.785 or 0.78, remember dz dt was equal to -3 at this point, meaning you could interpret this as the height dropping 3 feet or 3 inches per second as this particle moves. Notice as I increase t, the particle is moving downward. So this would be one interpretation of what dz dt actually represents. Now let's go back and take a look at finding dz dt using basic substitution to make sure that we get the same derivative. What I mean by that is we're going to replace x with 2 cosine t and y with sine t, and then find dz dt. And the result should be the same. So z is going to be equal to 4 cosine squared t plus sine squared t plus 1. Let's go ahead and determine this derivative here. We're going to have to apply the chain rule here. Multiply by 2. That's going to be 8 cosine t times the derivative of cosine, which is negative sine t, plus the derivative of sine squared t is going to be 2 sine t times the derivative of sine t is going to be cosine t. So dz dt is going to be equal to, now these are like terms again, this is negative 8 cosine t sine t, this is positive 2 cosine t sine t. So our derivative of course is the same. We have negative 6 cosine t sine t. And that should make sense whether we use the chain rule or we use substitution, our derivative should be the same. Let's go and take a look at one more. What I want you to notice on this one is we have w defined in terms of 3 variables, and we have a single parameter for x, y, and z. So when there are additional variables, we can just extend the chain rule. We would have dw dt equal to the partial of w with respects to x times dx dt plus the partial of w with respects to y times dy dt plus the partial derivative of w with respects to z times dz dt. So let's go ahead and apply the chain rule here and see what we get. So the partial derivative of w with respects to x, treating y and z as constants, we'll have z plus y plus 0, or z plus y, times dx dt. Be careful here, u is going to be negative t, so we'll have e to the negative t times negative 1, or negative e to the negative t, plus the partial of w with respects to y. This would be 0, this would be x, and this would be z. So we have x plus z times dy dt, that's going to be e to the t, plus the partial of w with respects to z, so we'll have x plus 0 plus y, or x plus y. For dz dt, we'll have the derivative of e to the t minus e to the negative t. That's going to be e to the t, and then minus e to the negative t times negative 1. That'll become plus e to the negative t. Now that we have dw dt, we're going to go ahead and write it in terms of t now. So we'll perform substitution for x, y, and z. Z plus y is going to give us 2 e to the t minus e to the negative t. Multiply this by negative e to the negative t plus x plus z times e to the t. Well, x plus z, we have two terms that are opposite, so we'll just have e to the t times e to the t. And then x plus y is going to be e to the negative t plus e to the t plus e to the t plus e to the negative t. Now let's go ahead and multiply this out and then simplify it. Now looking at the exponential parts, we're going to add the exponents. That's going to be e to the 0. That's going to be 1. So we have negative 1 times 2. That's negative 2 plus e to the negative t plus negative t is negative 2t plus e to the 2t plus, and here we're going to have to FOIL this. So let's see what we get. We have e to the negative t times e to the t. That's 1. And then we have e to the negative t plus e to the negative t. That's plus e to the negative 2t. And we have plus e to the positive 2t. And then we have another 1. So let's go ahead and write it. Let's go ahead and finish this up. A lot of things simplify out here. We have plus 1, that's 2. There's negative 2. And then we have some like terms. We have 2 of these and 2 of these. So dw dt is equal to 2 e to the 2t plus 2 e to the negative 2t. And that's all we have time for in this video. In part 2, we'll talk about when x and y and even z are defined in terms of two variables. Thank you for watching.